Okay, so let's say we've got a researcher who believes, for some odd reason, that the firstborn twin is smarter than the secondborn. If we want to test this claim, so it sounds like a hypothesis test, right? The researcher has a hypothesis. We're going to test this at the 0.05 significance level. We could also say the 5% significance level or the alpha equals 0.05 level. We've seen these sample differences before. We did a confidence interval for this paired data. So we go to stat, edit, we put this data into list 1. I've already done that for us. And then we say, okay, cool, let's go back to stat and over to tests, and let's figure out which test we've got. So we don't have proportions, so 5 and 6 are out. We don't have 2 samples, right? We actually may have started with 2 samples, but we took all of the firstborn and paired them with their respective sibling and did firstborn minus secondborn. So paired data gives us 1 data set. That's the set we see in front of us. Because we do not know the population standard deviation, it's not a z-test, but rather a t-test. So that's the second part. Whoops, bring it back there. So that's a t-test. We can either put in the data or put in the stats. Right, the stats would require us to kind of know all of these different pieces. Since we have a list, we're going to use data. So our data is in list 1, frequency is 1, mu naught, so this is the null hypothesis, right? Our null hypothesis is basically that the IQs are the same, right? We have no reason to believe initially that there's any difference. Now the researcher, this is the alternative hypothesis, the researcher believes something different. So just in terms of words, we would say that the IQs are the same, right? The alternative hypothesis that the researcher believes the firstborn IQ is larger because they're smarter than the secondborn IQ. So that's our alternative. And so what we're saying is that, or another way to frame this, right, is firstborn minus secondborn is greater than 0, right? So that's just from taking this secondborn IQ, subtracting it to the left side. And that's how we could get this alternative. So in our calculators, when we're going through and we're saying, okay, so 0 is, right, that firstborn minus secondborn equals 0, meaning they are the same. So that's where our 0 is coming from. And then our alternative, right, a reasonable alternative would just be that it's something other than 0. But this researcher, for some reason, believes the firstborn is smarter. So that's why we're choosing this third option, right? Greater than whatever we said up here. So greater than 0. And that's what we mentioned for our alternative over here. So we think it's greater than 0. Great. So we're going to calculate this. And it's going to give us a handful of things, right? It's going to give us our test statistic t, since we're doing a t-test. It's going to give us a p-value. Okay, so our p-value is 0.4663. That's a pretty large p-value. That's certainly greater than our alpha of 0.05, right? Because of that, our sample results are not rare, right? If the null is true, our sample results would occur, something like our sample results would occur almost 47% of the time. So we'll say since p is greater than alpha, we fail to reject the null hypothesis, right? We do not have statistically significant evidence to suggest what the alternative is and what the researcher believed. So we don't have statistically significant evidence to suggest the firstborn is smarter than the secondborn among twins, just to be clear. So there are, again, a couple ways to say that. The first is generic. We fail to reject the null. Remember that failing to reject does not mean we embrace it. So we're not saying we have all of this evidence that the IQs are the same, or that they're equally intelligent. We're more so saying we don't have evidence to suggest our alternative. All right, so we either reject or fail to reject the null. Again, there are a couple different ways that we can frame this, but this is definitely one of them. So we do not have statistically significant evidence.